Hi, everyone. Thanks for joining our webinar, Introduction to NuoDB. My name is Larita Ba, and I'll be the moderator for today's event. I'm joined here by Arif Kassam, our VP of Product, and Joe Leslie, our Senior Product Manager. We're going to just cover a quick overview of NuoDB, our architecture, and how it works. And then Joe's going to follow up with a short demonstration to really bring those concepts to life. In the end, we'll open it up for Q&A. You have at the right of your screen a GoToWebinar control panel. You'll have the ability to use the Questions tab to go ahead and enter into any questions. As those come in, we'll be logging them and respond to them at the end. We will be recording this session. It will be available for replay for those of you that want to be able to capture it, and we'll have the slides available as well. So with that, I'm just going to go ahead and turn it over to Arif.
Thanks, Larita. So let me start out by sort of stating who is NuoDB, why are we different, and why I believe you will be interested in looking at us. So NuoDB, we talk about ourselves like an Elastic SQL database. So what does that mean? That means the ability to combine the simplicity of scale out, both in and out, the ability to have continuous availability both within a single data center or across data centers or multiple regions. That also supports standard SQL transactional ACID database that you are used to for your OLTP applications, your transactional applications. We believe we provide a unique differentiator between traditional databases, cloud databases, as well as the existing NoSQL databases by enabling both ACID SQL transactions as well as the simplicity of scale out and availability for cloud deployments. So just a quick recap of sort of infrastructure and technology changes over the last few decades. We've gone from mainframe all the way out to sort of cloud and microservices architectures. And as you can see, the progression is obviously very simplified, but the progression basically shows the complexity of the architecture, the increasing in the number of servers, the connectivity between the different layers. They have all increased. But traditionally, the database, your standard transactional OLTP database, has been fairly, I don't want to say monolithic, but fairly stagnant in its architecture. Typically, you have a single server that's your main database server, and you may pair that up with some sort of secondary server for availability, for failover through some sort of log replication or through some sort of data shipping to that system. And then you may have a third server in a DR site that, again, is kept up to date through some sort of asynchronous log mechanism or potentially even at the disk level through a SAN or some other block shipping mechanism. I think, as you can sort of see, the application architectures have evolved. They've taken advantages of newer architectures, newer ways of grouping data, of grouping applications and servers. However, your options for databases in the OLTP space have been fairly limited. So what are we seeing with our customer base? Our customers are asking for quote unquote elasticity. And what we mean by elasticity is the ability to run the database in different environments, virtualized environments, container environments, different data centers, different regions, different areas in the cloud, on premises. So basically the flexibility to deploy a database in various environments. They want to be able to scale the database in and out dynamically without impacting the application. In this day and age, applications may peak. You may get a surge of users that you were not predicting, and you need to be able to scale the database without a significant amount of lift and shift of the servers. So the ability to scale out the database, similar to how you scale out web servers, is a very desirable driver for a lot of customers. And in this day and age of 24/7 web access and application access, everyone wants continuous availability. That's availability within a data center, so the ability to tolerate outages within a single data center or across data centers for DR purposes. In this day and age, everybody needs an approach that allows applications to remain available in the case of any sort of planned or unplanned outages. But customers are also saying, I want this without incurring a huge overhead of migrating an application to another database architecture. For example, NoSQL databases provide a lot of these capabilities that we sort of talk about in the elasticity category, but they do require a significant rewrite of the application. So our customers are saying to reduce the scope of changes, I would love to keep the existing SQL code that I've got, the ability to have ACID transactions, the ability to have durable data and guaranteed data durability for my applications. And so our customers are saying that they want to be able to elastically scale their existing SQL application into an architecture that supports the cloud environment. So we've sort of coined this term of Elastic SQL, which we believe bridges an existing market gap. The availability of traditional databases like Oracle, SQL Server, and IBM that provide ACID, transactions, SQL logic, data durability, those exist. And then the NoSQL world where Mongo and Cassandra and the others provide scale out, virtualization, zero downtime, better availability for specific environments. And they also provide a certain set of capabilities. But the combination of both those two is a market gap that we address. We provide this Elastic SQL capability that allows applications to maintain their acidity, their transactions, their durability, data durability, while taking advantage of the newer technologies and newer capabilities of Elastic SQL, scaling out the database, virtualization, containerization, and availability. We've coined this term Elastic SQL. We're not the only ones. We don't believe we're the only ones in this category. There are other vendors out there, and the next slide will sort of go into some details about the other options. But Google Cloud Spanner, probably, 6 months ago, announced their availability. We believe it sort of fits this Elastic SQL market and sort of capabilities. Also in that vein is Cockroach Labs, which provides an open source version of Google Cloud Spanner. And then probably a couple months ago now, Amazon also announced their Aurora offering, multi-master offering for Aurora, which also fits in this Elastic SQL capability. So this is a bit of an eye chart, and so let me try to orient you in this sort of comparison of the various offerings and the various capabilities. In the rows, we've sort of grouped rows into SQL applications, cloud deployment, and other use cases. In the SQL rows, there's obviously the need for anti-SQL, the ACID guarantees, and being able to easily migrate existing SQL applications. In cloud deployment, it's scalability, active-active, so the ability to run workloads actively across multiple data centers, and flexible cloud deployments, the ability to deploy in different cloud environments, on-premises, and cloud environments, sort of a hybrid approach. So the flexible cloud deployments talk about sort of multi-cloud or hybrid approaches. And then other use cases, which are non-relational data, streaming, and heavy analytics or machine learning even. The columns are your traditional databases and database as a service or cloud offerings. The NoSQL space, which again, Mongo and Cassandra are two of the bigger ones. And then the four companies in what we think are the Elastic SQL market. So if we go back to the sort of traditional relational databases, as you can see, they're perfect in the SQL application space, right? Obviously, that's where they grew up and that's where they come from. They get partial check marks for migrating SQL applications because everyone knows moving from one database to another database can be done. It does take a fair bit of work and consideration, but it can be done. On the cloud side is where they sort of fail over and sort of have limitations in elastic scalability, active-active, flexible cloud deployments, and other use cases. You can use them for streaming and or IoT or other data sources like JSON, but traditionally they're not the best in those modes. The cloud database has a partial check on elastic scalability just because for all intents and purposes, even though it's a scale-up architecture for cloud databases, they do provide this idea of scaling on demand. In the back end, they are switching the database server around for you, so it does look elastic, the ability to scale up pretty dynamically. But ultimately, it's a lift and shift from a smaller server to a larger server, so it's still scale-up architecture. The NoSQL column, obviously great on elasticity, active-active, flexible deployment, different use cases, but they lack the SQL capabilities. A lot of these vendors are adding SQL as a sort of language that they can work with. So the NoSQL vendors are adding SQL, but they're typically limited in what they can support, depending on the types of joins you want to do or other types of operations that are standard in a relational database. And so it's basically a bolt-on to their existing architecture. And then if we look at the Elastic SQL market, you've got Google Cloud Spanner, Cockroach, Amazon Aurora Multi-Master, and then NuoDB. Each one of these has a slightly different architecture, so they're not the same, exactly the same in their capabilities, but generally they provide the ability to elastically scale out your database, the ability to take an existing SQL application and migrate it. However, for both Google Cloud Spanner as well as Cockroach, they really only support SQL from a select or reading perspective. Any updates, changes, or deletes to the database require calls through their API. So there would be still a fair bit of work on migrating a SQL application to change how the data is accessed or changed using those two solutions. Obviously, Google Cloud Spanner is only available in the Google Cloud. Cockroach Labs allows you to put the Cockroach DB on different systems. And then Amazon Aurora is also only available in AWS. They don't support a hybrid approach, sort of on-premises and cloud environment or multi-cloud environments that we're seeing that customers are sort of driving to today as well. Just very quickly on NuoDB, obviously we got great SQL support. We support elasticity and active-active and flexible cloud deployments, but we are an operational database. We don't generally target huge analytical workloads or streaming workloads or sort of a document store type of use cases. We are targeted at operational transactional applications. So the next few slides, I want to sort of quickly walk through some customer use cases just to give you an idea as to why customers are selecting NuoDB. The first customer is Dassault Systems. Dassault is the largest European software company after SAP. They are a software company that provides sort of CAD/CAM, PLM, product lifecycle management software to a lot of manufacturing customers. They have an existing $3 billion business. Like a lot of vendors out there, their traditional business has been to selling to customers who would deploy their software on premises and configure it to run within the customer's data center. As with a lot of vendors today, they are providing a SaaS offering. So they're migrating all their applications to a cloud, to their own cloud. And as part of that migration, they come to the realization that they need to select a database that they're going to manage as part of the whole stack. So they traditionally ran on Oracle and SQL Server. They selected NuoDB because of our elastic capabilities, the ability to easily scale up their cloud infrastructure based on demand. As their customers were growing and more demand was growing in their cloud, they needed a database solution that could easily meet that demand elastically in or out. And so we provided the ability to work in their cloud, the continuous availability, as well as the elastic scalability. From a benefit standpoint, significant cost savings over Oracle, and their data layer, their data capability becomes a competitive advantage for them. They can provide a certain availability guarantees for their solutions to their customers that they could not do with their existing database infrastructure. The second customer we want to talk about is a smaller company called Move Medical. Move Medical provides medical device and case management software. Again, like both Eaux and other companies, they are migrating their solution from an on-premises solution to a SaaS solution. Being a smaller company, they didn't understand or weren't able to predict how many customers would jump on the new platform. So their understanding of data requirements, sizing requirements was sort of ambiguous at best. And so again, they looked at us to help solve this idea of scaling on demand. So rather than buying a data platform which would cost them a significant amount of money for a potential performance requirement or demand growth that could come down 3 years later, they would rather select a database platform that they could grow as their demand grows, as their customer base grows, so that they can easily adopt to capacity over time. So again, the Elastic scale out was a number one driver for the selection for NuoDB. Continuous availability, as well as the very low cost of migrating their existing application to NuoDB. It was a very simple migration from their existing database to NuoDB. They looked at other vendors. They also looked at Aurora prior to having, obviously, the multi-master stuff. They looked at Oracle and suggested that for their use cases, we had a lower TCO than both Aurora and Oracle. We simplified their disaster recovery and failover situations, and we were able to get them to market a lot faster than if they had gone to a NoSQL database. So that was sort of a quick summary of sort of our customer use cases. Again, this is sort of a sampling of our existing customers, as well as sort of as a company what target we are going after. So going a little bit deeper into the technology. The diagram here on the right sort of talks about a traditional database. So a traditional database is a single process that typically does both SQL processing, parsing, query execution, as well as storage management. So the entire process manages the complete stack of taking the query, optimizing it, parsing it, optimizing it, and then executing it, and also storing the data. The insight that our founders had when they created NuoDB is that you could split that processing up into two separate services. So in NuoDB, we have a layer called our transaction engine, right? So this is the processing layer where clients connect up to, execute SQL against, and this is a fully in-memory, fully distributed transaction engine. Right? You can think of it as an in-memory database, a distributed in-memory database. You could also think of it as a distributed cache. Right? Effectively, each transaction engine builds up a cache of data based on access patterns that clients connect to it and drive through the transaction engine. The second layer is what we call our storage management layer. This is the layer that provides the durability guarantees for the data. In traditional architectures, you may have a traditional database that has a caching layer built on top of it. In those types of architectures, the application is responsible for either a write-ahead cache or write-beside cache type of, or a write-through cache type of architectural considerations. And so the application has to make sure that the cache that they're using is consistent and coherent with the database and the data being stored in the database. The beauty of NuoDB is that we combine both the cache and the durability in one single logical database, and we take care of the cache coherency between the transaction engine and the storage manager for you. So you don't have to worry about ensuring that the data is up to date in the cache or writing that data out durably to a storage manager. Each of these layers can be scaled independently of each other. So if I have an application that is read intensive, I could scale out the transaction engines to get better throughput on that particular workload. Or if I've got a workload that is write intensive, then you could have the storage managers either be fully redundant copies of the data or have it partitioned or have the data sharded across multiple storage managers so that you can scale out your I/O workload across multiple servers. The entire system, the multiple transaction engines and storage managers look like a single logical database to clients. The clients can connect up to any single transaction engine. There is no head node, there's no master node in our architecture. They can connect up to any one of these transaction engines and execute any query to access all the data within the environment. Because this is a fully distributed database and a distributed architecture, these processes can be distributed across multiple servers, multiple data centers, or regions for availability. And we also support the idea of rolling upgrades. So we can take a single process down, upgrade that process to a newer version, and then continue on through all the systems without having any application outages for a rolling upgrade experience for the application. The key behind the NuoDB architecture is what we call the durable distributed cache. So the cache obviously puts the data close to the application. It puts it in memory, which makes transactions extremely fast within NuoDB. Right, the cache can be located right at the Java server, right beside where the calls are being made by the Java server, or they could be put in other areas where the data is needed. The caches are fully transient and built on demand, so you can spin up these transaction engines as you need them or shut them down as you don't need them. They're fully consistent. It's a fully peer-to-peer mesh between these transaction engines, so they can make sure that the data is consistent across all these transaction engines. Because it's a distributed cache, we don't explicitly require customers to shard their database. We don't explicitly require the customer to cache the data in specific patterns. The cache is built up as the clients connect to the TEs and access the data. They're fully peered across the environment. The failure of any one transaction engine doesn't have any impact on the other application connections. And the data is distributed across all the transaction engines. We also don't require the full data set to be in memory, right? Because we have a storage manager, some of the data could be on disk because it's not used at all. It could be archived data. It could be data that's rarely required by the application. So we don't require to have enough memory to fit the entire database in memory. And the durability also provides guarantees that the data is fully durable and available on the case of restarts or outages, just like any other transactional database. This is another logical view of NuoDB. So again, starting from the top, we have standard database connections. JDBC, ODBC are standard database connections. So again, from an application point of view, we look like just another database, right? From a management perspective, we have a RESTful API that integrates with a number of management utilities that exist out there in the marketplace. We do have our own command line interface to manage the environment, but generally customers integrate the management of NuoDB into their existing management infrastructure through the RESTful calls or command line arguments. As part of the NuoDB database, so we talked about the transaction engines, we talked about the storage managers, there's obviously also an administration component to NuoDB. These are separate processes that live alongside of the database processes. They manage the domain, which is the representation of all the transaction engines and storage managers for a given database. And then we also manage load balancing across the transaction engines through our administration layer. So again, from a client perspective, they connect up to NuoDB as a single logical entity, and they could be directed to any one of the number of transaction engines that exist in the environment. We have load balancing policies to keep it within a data center, or if they want to go across data centers, that can be set up as well. The distributed durable cache is is available at both the TEs and SMs. So the SMs are also memory intensive, but they do also have a disk associated with them, whereas the TEs are fully in memory. The transaction engines, as I mentioned before, do the SQL parsing, the optimization, the execution, and cache management of the data. And the storage managers manage the durability of data on disk, as well as in memory for fast access. We're fully ACID compliant, as well as we are an MVCC database, a multi-version concurrency control database, allowing for increased readers of data so that you can get additional concurrency from your applications. This is a typical network diagram within a single data center, right? So you've got your transaction engines, which are processes represented by the dark green systems. Circles, they do transaction processing. As I mentioned, the applications connect up to the transaction engines. And then the storage managers are below. There is a little bit of a small little error here. The two SMs should be both light green, not dark green. But again, they can be dynamically scaled out independently. So as you need them, the hashed circles represent servers where you can deploy additional transaction engines or storage managers. They could be on physical systems. They could be in containers. They could be running in a container orchestration platform like Kubernetes or OpenShift. They could be running in virtual systems through VMware or other virtual environments. These processes, again, it doesn't matter to us how they're deployed. They network up together and create a peer-to-peer mesh across the environment. So with that, Joe is going to take a few minutes to go through a demo. So just before Joe goes to the demo, just a quick overview of what the demo is going to show. We're going to show a single NuoDB domain, which will be consistent of 3 transaction engines and 2 storage managers split across 3 different availability zones. So there's going to be one TE and one SM in availability zone 1, another TE, another SM in availability zone 2, and then a single TE in availability zone 3. Each of these zones will also have an administration component called the broker, and the broker is what creates the load balancing capability for the application. So the applications connect up to the broker, and then the broker decides how to connect up to the transaction engines based on the load balancing algorithm specified on connection. Okay, Joe.
Great. Thank you, Arif. I'm just going to take a moment to switch screens. Hopefully you should all see my screen. And yeah, I'm going to go ahead and demonstrate the environment that Arif just described. Just taking a moment to, again, emphasize the ability to deploy NuoDB in a very flexible manner. Arif was sharing that you can deploy NuoDB in sort of a bare metal or virtual machine environment. You can deploy NuoDB in like a hybrid cloud environment, and also, of course, a regular cloud environment where typically microservices and containers are used to deploy the application. So for today, I'm going to demonstrate the latter. We're going to show how we can deploy using Docker containers. I'm going to use Docker Run today, and it will show you what it would be like if you were deploying NuoDB in a cloud-centric container environment. So I've got this command here, deploy NuoDB zones, and it's going to deploy exactly what Arif was referring to. So the first parameter shows 3 zones. The second is indicating the number of zones that we want to include persistent storage managers. These are separate copies of the database on disk. And our database is called test, and the username and password is DBA and goalie. So once we have this command set, we can go ahead and let it create our environment. So it's now off to the races of doing that. You'll notice it's starting the NuoAdmin service containers, and it created 3 of them for us because we asked for 3 zones. Each one is created with its own volume, its own disk storage, as we see here. And you'll also notice that each time it creates a container, just to describe what you're seeing here, the containers are created with these very long lines with lots of letters and characters. But once it created the domain, which is made up of those NuoAdmin broker processes, we have now created the database itself by creating database containers. So highlighting the first container, as described, it includes both a storage manager. Again, this is a copy of NuoDB on disk. This is the persistent archive on disk. And then also that transaction engine component Arif was describing, the one that's responsible for processing the SQL, making the SQL connections and running the SQL themselves. So we see there was also the second zone created. Again, it also has the storage manager component and a transaction engine. But you'll notice the third one just has the transaction engine. So there is no copy of the database in the third zone. So if we were to just take a look now using the NuoDB command line interface, we'll take a look at what we have. Before I go ahead and describe that, one point of note is we've created the domain and we've created the database, but we don't yet have any data in our database. So while I'm describing the domain and the database, we're just going to come over to another window and we're going to create some data that we can use a little later in our presentation. So while that's creating data, let's describe for you what you see here. So the first part, we see the domain consists of servers. These are the admin service processes, and the admin service processes, typically you're going to have one per host or one per process space within your environment, and they have specific jobs that they're responsible for. They're responsible for, as Arif had mentioned, the load balancing aspects. When an application requests a connection to the database, the admin server is responsible for finding a transaction engine that meets the requirements of that particular application, be it local or they have some certain characteristics, either processing or memory, that would make that transaction engine uniquely qualified to service that particular application request. As well, the admin processes are responsible for, within a distributed system, and again, NuoDB is a distributed SQL database, all of these broker and admin service processes are talking to each other, communicating, and ensuring that the domain is in a healthy state. They're responsible for the adding and the removing of physical hosts within the environment. Lastly, they're also responsible for managing the database processes within their process space or on their host machine. So we have the three servers, the NuoAdmin 1, 2, and 3. We see that they are all active and they are all connected. And within our system, NuoAdmin 1 is our leader. But again, I want to make the important point that the NuoDB system is a true master-master model, meaning in the event of a failure, if we should lose our lead broker, then the others, while currently following, are as powerful and will quickly elect a new leader. So again, NuoDB is a very redundant as far as process and making sure that we are always delivering continuous availability in the event of a failure. And likewise, we see that as we've created our database below, we see on zone 1, if you call zone 1, which is up and running, has both a storage manager and a TE. Now, we could have created our database with just that much, and we would have had a working database. We would have had one transaction engine and one storage manager. But we would not be fully redundant, and we would not be protected in the event of a failure. As soon as we created the second set of containers in zone 2, we now have a fully redundant database. We have 2 storage managers, so we have 2 full copies of our database, and we have 2 transaction engines, one in zone 1 and in zone 2. And then just to further show the ability to scale out in our demo, we're also showing that we could create a 3rd zone where we added just a transaction engine. So we have 3 transaction engines that can service application requests. Now we have just added some data into our system. So what we can do is we can go ahead and access some of that data and start demonstrating some of this capability. So I'm going to bring back another command. This one here. This is our run SQL command. This is really just a demonstration application, and what it does is it's going to connect to the database, but you'll notice in this first parameter, I'm telling it how to connect. I'm saying go ahead and connect to data center 1, zone star, meaning zone, I don't care. You can connect to any one of the zones you want. This is going to leverage the NuoDB round robin load balancer, meaning it's just going to randomly request and provide a TE for this particular application. It's going to run this little SQL program, and the 0 simply means just keep on running it until we stop the program. So if we go ahead and run this, you'll notice what it's going to do is it's going to connect, and because we have chosen round robin, you'll notice immediately that it's connecting to different transaction engines. Why? Because we said go ahead and connect to all that are available. So we see TE 1, 4, 3, and it will continue as this application runs to provide a random set. Now, likewise, as you would probably expect, if we wanted our application to target a particular zone, we can tell it to do that as well. So here we're going to run the application, and we're going to say, I only want to connect to zone 1. So only provide me the transaction engine that is in zone 1. Now, if we go back and we remind ourselves, zone 1 is using transaction engine 1 right here. All right, so let's go ahead and run the command. And because we're asking for zone 1, we would fully expect that it is always going to return test TE1, right? Because that's, we want to, in this case, we want to connect to, for example, a transaction engine that is local to our application. Now, likewise, if we wanted, we could, to further the point, we can connect to any zone we want. So now I'm going to connect to zone 2, which, if we remember, zone 2 had transaction engine 3. So we see that here it's connecting to transaction engine 3 reliably each time. And we can go back to a round robin if we want to just go ahead and randomly hand out transaction engines as the application requests are being made. And then we'll see transaction 1. It is random, so it's not going to always go from one to the other, but it will randomly pick up based on the randomness of handing out transaction engines. Okay. All right. Let's go ahead and demonstrate some of the SQL capability of NuoDB. Many of you are familiar with SQL databases, and you may want to see NuoDB in a more graphical environment. Now, when I run NuoDB, I typically use several different universal graphical SQL run tools. Today, I'm demonstrating for you DB Visualizer, and it provides for you a very common feel of any other graphical database tool that you may have used. So we just created this set of tables. This is the NuoDB hockey database, and we created these tables, and I wanted to show you some common views that you may be familiar with. Here's a very common entity relationship diagram where we show the tables we created along with the table columns, their data types, and the primary and foreign key indices, all presented for us in a presentation that I'm sure you may be very familiar with. Likewise, just to demonstrate some of the SQL capability of NuoDB, I have for us prepared several SQL statements, and so you can get the flavor and see that, yep, NuoDB is a SQL database. It runs ANSI standard SQL. In fact, it supports many variants of the ANSI standard syntax. Let's go ahead and demonstrate some of that. So here we have a SQL statement that's going to join several tables in the hockey schema. I'm just going to go out, and this one actually determines within this database the top hockey goal scorers in a single season. But as you'll notice, and if you're familiar with some basic SQL syntax, you'll notice here we have sort of the older style SQL 89 syntax where we use the from clause to join lots of tables, and then within the where and clauses, we create our join clauses. But I can run the same SQL using newer style. So we support both the SQL 92 and 99 standards. Here is one where we're using you may have written your SQL using join on syntax, and it's going to return the exact same data. SQL statement's written slightly differently, but it returns the same data. Likewise, in this third example, we're using the join using clause, right? So NuoDB supports common SQL, and why is this important? One of the things that Arif had mentioned was the lower cost to migrating your applications. Well, because we support such a rich variant of the SQL ANSI standard, you will have very little SQL modifications to make as you are migrating your applications to NuoDB. So hopefully that gives you a good flavoring of what you can expect with NuoDB. We would encourage you to download our community edition and try all this out for yourself for free. But at this time, I'm going to go ahead and conclude our demo.
Thanks, Joe.
You're welcome, Marie.
So just to quickly recap with the sort of last slide, and then we'll open it up for questions. So NuoDB is what we refer to as an elastic SQL database. We provide, again, the ability to elastically scale out in dynamically, as well as availability across data centers or within a data center for availability purposes. Shown here on the right is a sample of some of our customers. We went through some of the customer use cases in this presentation. There are other customers not shown here for obviously privacy reasons. We've been in business since 2010. Creating a database is not a simple task. The commonly held view is it takes about 7 years to create a database, and we've been at it about that time. We believe we have a very good database that can meet a lot of use cases and a lot of customer demand. The management team is filled with executives who've been working in the database industry for a number of years. Obviously, this is a patented database that we use, and we're headquartered in Cambridge with offices in London and in Dublin. With that, I think I'll transfer it over to Rita for questions.
Great. So we do have a few minutes left for questions. We've had a couple that have come in through. But if you have any questions, please feel free to add your question to the GoToWebinar control panel. One of the first is just a logistics question, which I can answer, and that's whether or not we are offering this recorded session available for later evaluation, or if you want to share it with peers. Absolutely. So we'll be sending that out after the event. We also run these on roughly a monthly basis. So, you know, it'll be similar content over every month. So if you have customers or friends or peers that you want to introduce to NuoDB, please feel free to direct them to that. The next question is, you know, do you think that NuoDB is better for net new applications or for existing applications that you're porting to a new environment?
That's a good question, and from our customer base, we have both, right? So we have customers who are creating new applications using NuoDB. In those use cases, they started with needing a SQL Server database, and they selected us as the database to start with. Obviously, that's easier for a lot of different purposes because the development is working side by side with us and building on top of a new capability and leveraging the benefits of NuoDB right from the start. However, we do have a lot of customers who have existing SQL applications that want to do some sort of digital transformation, have a digital transformation initiative, who are moving to the cloud, moving to containers and microservices, and need a database that can help them. And rather than incurring the additional risk of porting the entire application to a different architecture or a different system, they have selected NuoDB to reduce the risk of that initiative and move to a standard SQL system that also allows them to take advantage of the newer architectures. So we're seeing both types of usage, both new and existing. I don't think that there is one or the other. Both use cases are perfectly valid.
Great. A couple of questions here on partitioning. What types of partitioning does NuoDB support? Hash, range, etc.
We have range partitioning today. We will be building out hash partitioning in the future, but today it's basically range partitioning.
And then regarding partitioning, how does that change with node additions and reductions?
That's a good question. So we've got two levels of logic here. We have your standard partitions where you can define standard table partitions where you can define how the data is partitioned within the table. And then the second part is what we call storage groups. Storage groups are the logical entity at the storage manager layer for a given partition. So for example, if I've got 10 table partitions, I can allocate those 10 table partitions either to their own individual storage groups or have 2 in each storage group. And then those storage groups then are assigned to a particular storage manager. So if I have 10 storage managers, I could then have one storage group on each storage manager and a redundant copy of another storage group on that same storage manager. So we provide a lot of flexibility for customers to architect their environment from a table partitioning and storage group management layer to get both benefits from a table partitioning view as well as a scale out at the storage layer and I/O benefits.
How does NuoDB compare to other databases when being used in a microservices architecture?
So in other databases, well, I'm just going to take some of the open source databases like MySQL or Postgres. Typically, what's happening out there in the industry today is there's sort of two different axes that customers are sort of still playing with. One is, do they put the database within the microservices environment or outside the microservices environment? So a lot of customers who are just starting with microservices will deploy a container microservices farm either on OpenShift or Kubernetes or some other platform, but that would only be containers for the application, for the actual services of the application. Those containers, if they need data access, would then connect up to a database that exists outside or is deployed outside that environment. That's a simple way to do it. That provides the benefits of microservices for the application, but then still leaves the database as a orphaned child, if you will. Other customers are then taking that and containerizing the database and putting that into the environment. Then they have to figure out how they're going to persist that data, whether that data is going to be persisted within that container or whether it's going to have persistence outside of the container for durability and redundancy. The problem with taking an existing database like MySQL, Postgres, or even Oracle for that matter, and putting it into a container is it's still a very heavyweight system, and they don't provide scale out capabilities. I still need to run a single virtual environment, virtual system, container system for my database, and all my services that use that database would then connect up to it. I can't really move it around. I can't scale that out by adding more containers. The only way I can scale that database processing is putting that container on a bigger system. That sort of defeats the intent and purposes of containers, the ability to dynamically move containers around and gain performance advantages by just adding containers. And so that's where the NuoDB architecture, the scale-out architecture, is a significant advantage for NuoDB in container environments. Because of our architecture, you can deploy new containers to address performance concerns for any particular service for that database. And so we basically fit very well with the tenets of a microservices architecture. We do have two services that are separate that can be deployed as containers, and they can be independently scaled out as needed.
You mentioned hybrid cloud earlier. Can NuoDB work across multiple different public clouds?
Yes, so we support both AWS, all three, AWS, Azure, and Google Cloud Platform. We have an existing customer that uses in Europe a fourth cloud provider called Outscale. And so they're using NuoDB in AWS and in Outscale together. We also have customers that are testing out deploying NuoDB from an on-premises and a cloud deployment perspective, so hybrid from not just multi-cloud, but hybrid from on-premises to cloud.
Do the machines that are running NuoDB, do they need to be dedicated to NuoDB, or can they be used for other things as well?
So you could you can run NuoDB. So there's a couple answers. You can run NuoDB in a multi-tenant environment. So you could have multiple NuoDB processes all supporting different databases and different applications running on the same system. So for us, it doesn't really matter what else is running on the system, so long as we've got dedicated or allocated CPU and memory and disk associated with that, so long as there's no conflicts in resources. And to that end, you could also have NuoDB running. We have certain customers who have deployed an application server and a transaction engine on the same server, right? That again, that creates a very close bond and very close linkage to the data that application server needs for very, very fast, low latency queries and access to data. And so you could run applications and transaction engines on the same host.
Great. I'm afraid that we've actually run out of time, so I want to thank everybody for joining us today, as well as Arif and Joe for presenting and showcasing that demonstration. For those of you that have additional questions, please feel free to respond to the email that will include this recording after the event. But in the meantime, thanks for joining and have a great afternoon.